So I'd like to welcome all to our 2016 seminar series. As you know, our distinguished seminar series aims to invite to our department distinguished speakers from all around the world, have them visit our department, learn about our research and teaching activities, meet with academic colleagues and the research groups, and get an understanding of the breadth and depth of the department. It is also a unique opportunity for us to learn from their ongoing research, be inspired by their ideas and vision, and find out where the trends of chemical engineering are moving towards. We started this series with Professor Venkatasubramanian from Columbia University, who delivered the Roger Sargent Lecture. Today's distinguished speaker, which is a great pleasure and honor for me to introduce, is Professor Samson Jenekhe from the Department of Chemical Engineering at the University of Washington in Seattle. Professor Jenekhe graduated from Michigan Technological University with a bachelor's degree in 1977. His graduate studies were then conducted at the University of Minnesota, where he received a master's in chemical engineering, an MA in philosophy in 1981, and a PhD in chemical engineering in 1985. Professor Jenekhe then moved to industry, specifically at Honeywell, at the Physical Sciences Center in Minneapolis. And then he started his academic career at the University of Rochester, where he held positions as assistant, associate, and full professor of chemical engineering and material science and chemistry from 1988 to 2000. And that's where I met Professor Jenekhe when he was one of my professors during my PhD tenure there. In 2000, it was actually the same year that I moved to London, Professor Jenekhe moved to the University of Washington to assume his position as the Boeing Martin Endowed Professor of Chemical Engineering and Chemistry. His broad research interests are in the chemistry, physics, and engineering applications of conjugated polymers, organic semiconductors, electronic and optoelectronic devices, materials and devices for solar energy technologies, self-assembly, and soft nanotechnology and polymer science. Just to give you a measure of his research achievements, they can be summarized in over 300 journal publications, which have received over 22,000 citations with an H index of 82. And I think that's an astonishing accomplishment in itself. He has also edited 3 books and has been awarded over 26 US patents. Thomson Reuters named him among the top 40 on the worldwide list of top 100 material scientists for the past decade of 2000 to 2010. And in 2014, again, Professor Jenekhe was named as a highly cited researcher in material science. He has served on the editorial advisory boards of many journals, including Macromolecules, Chemistry of Materials, Chemical Engineering Journal, and Micro and Nano Systems. He is the scientific editor of Molecular Systems Design Engineering, a new journal from the Royal Society of Chemistry and the Institution of Chemical Engineers, along with our colleague Claire Agyeman. Professor Jenekhe is a fellow of the American Association for the Advancement of Science in 2003, the American Physical Society in 2003, the Royal Society of Chemistry in 2015. He has been elected member of the Washington State Academy of Sciences in 2013, and in 2014, he was the recipient of the Charles M. Stein Award from the American Institute of Chemical Engineers. Please join me in warmly welcoming Professor Sam Jenekhe, who is going to share with us his experience and research work on plastic electronics and photovoltaics. Sam.
Thank you very much, Sakis. I'm really delighted to be here visiting your department today. It has been very stimulating and I have enjoyed it very much. So now I'm going to take some time and share with you some of the work that we do in my lab at the University of Washington. All right, so the area of plastic electronics is one that is quite familiar on this campus, especially for people in the chemistry and physics department, and also material science. In putting together my presentation, my talk here, I'm directed largely to chemical engineers. This is a chemical engineering department. So I may necessarily look at something in a simplistic way to provide the necessary background. All right. So we all know, you all know, that in the field of electronics and information technology, silicon is the king. For a very long time. One very important metric, which I want you to take away from this, is that ability of charges to move in crystalline silicon, which is a very important, that's not the only one, but a very important part of why it has been so successful as the workhorse electronic material is these numbers here. The units doesn't really matter, but just to give you an idea of silicon-based electronics, and we're going to be comparing as we go on organic semiconductors with these numbers. All right, so what you probably do not know, and perhaps some of you do know, is that carbon, like silicon, so carbon just above silicon in the periodic table, has found some application in electronics. So the very first, perhaps very successful one in the early days is this. The photoreceptor, which is at the heart of photocopiers, fax machines, and other devices that I'm sure you have used, even if you did not know that at the heart of that was organic semiconductor that really made that possible. In this case, if you look at the same numbers with the same unit, the carrier mobility is not very high. And one of the reasons for that is the molecule that we have here, abbreviated TAPC, it is a dimer of triaroamine that is able to transport holes, transport charge. It's dispersed in the matrix of a conventional polymer such as polystyrene. And the material overall is amorphous, highly disordered, and you have hopping from side to side, and as a result, mobility relatively low. However, for this particular application, that's great. And the photoreceptor, the coating that you see here is quite interesting. They use precision deep coating to form the coating on that with this organic semiconductor. All right, anyway, with the discovery of conjugated polymers, which many of you probably know, typical examples are shown here of these polymers. The very first one, polyacetylene, discovered by this guy. With this discovery, you notice now that the carrier mobility have gone up because the structure of the polymer is such that certainly a lot more rigid, and you can create relatively more ordered, perhaps semi-crystalline material from that. And as a result, the electronic structure leads to a variety of electronic and photonic properties ranging from not only ability to transport charge, but light emission, light absorption, and so on. So clearly, opening up the potential for a variety of electronic and optoelectronic applications, of which today I'm really going to focus on a couple of these areas that I will be coming to shortly. All right, so these are some of the applications specifically taking advantage of conjugated molecules that are able to emit light very efficiently and also to transport charge. As you can see here, these devices made on organic light-emitting diodes, or OLEDs, have enabled a variety of displays that more and more people are beginning to use these, ranging from small screens that we find in our smartphones and other devices, to very large screen TV as shown here, or lighting applications that are also now becoming commercial. All right. So in my group, what we do very broadly is to combine molecular design and synthesis of material with ability to look at structure property relationships in these materials to make devices, to create nanostructures and find a way to control the nanostructure with the hope of enabling and developing more efficient electronic devices. All right, so what I'm going to do is use two areas, examples in two areas. One is the OLED. I've already shown you the application. A little bit of what we've done in this area, and then I will move to the plastic photovoltaic area. So this is the first the discovery. Was made at Kodak. It's my Kodak by Chin Tang, fellow Chin Tang, based on the small molecule here, aluminum quinolate, or AlQ3. And interestingly, you notice the same molecule here, TAPC. Both Kodak and Xerox were for many, many years quite vast in creating and using molecules such as these to make photoreceptors, and Chin Tang turned to make organic LEDs that were relatively efficient, low voltage thin film devices. And then, of course, shortly after that, nearby here in Cambridge, Richard Frank's group demonstrated that the conjugated polymers that you saw earlier can also be used to make thin film LEDs, polymer LEDs that are also relatively efficient, and then, of course, the rest is history in trying to exploit this technology in a variety of applications. In my lab, what we have contributed the most to this field of OLED for display and lighting is in developing both materials and the processing of these materials, particularly electron transport materials that allow injection and transport of electrons to make these devices efficient. We've also developed materials that emit light across the spectrum, but perhaps the one example that I'm going to show, which is at the time, a very challenging one is materials that can efficiently emit blue light, while at the same time being able to transport electrons as opposed to holes. So in the example shown here, we have quinoline oligomer, we call oligoquinolines, that are very easily made and purified to a very high degree without using any methods as catalysts. So it's all acid catalyzed, so they can very efficiently be made and purified. One of the reasons why it was very difficult making efficient blue LEDs was the difficulty in materials degrading over time, or if they crystallize or they pack very efficiently, that leads to new electronic states that can emit colors more reddish compared to the blue that you are interested in. However, these particular oligoquinolines, as you can see here, they emit very nicely in the blue region. And we were able to show that even when they crystallize, they did not pi stack. They did not form a structure that pi stack. And the reason for that is because of the side chains that are attached to the background. So that prevented the ability of the molecules to pack efficiently, and hence you can retain very efficient blue. And furthermore, as you can see from here, the glass surface temperature quite high, which means that they are robust and can be used very well in OLEDs devices. All right, so we made devices in our lab. This is a typical structure of the device, and you apply voltage, and then you get blue emission from that, as you can see here. They can be very, very bright, as seen here with a picture of pixels of the devices, and quite bright. And at the time, they were the most efficient blue OLEDs. All right. So what I show here is a typical that device in the previous slide, where we are progressively increasing the voltage, and as you can see here, they become brighter and brighter. And this work was done in a center, NSF-funded Science and Technology Center, that focus on developing functional electronic materials. And our collaborator, members of the center, Bernard Kipling Group at Georgia Tech, in the electrical engineering department, decided to incorporate these new blue emitting materials in actual display to demonstrate the basic concept. And as you can see here, it's basically spelling out the name of center, NSF, STC, and then the MDITIR, blue OLED display. We have also done a lot in developing these oligoquinolines, in this case dendritic structures, that are aimed to transport more as electron transport materials than emissive materials, and they can be processed from both solution and by vacuum deposition. And this has led to developing very efficient blue phosphorescent LEDs or PHOLEDs as opposed to fluorescent devices. In this case, we're using iridium triplet blue emitter here, whereas the dendritic oligoquinolines are used as the electron transport material. This is all deposited sequentially from solution, leading to very efficient devices, also very, very bright. And as we can see in a color coordinate here, right in the blue region of the CIE coordinate. All right, so what I'm going to do now is to quickly move and focus the rest of my talk in the area of organic or plastic photovoltaics, where I'd like to share with you what we have done more recently in this area. It is also well known to you what photovoltaic devices do. Basically, they convert sunlight to electricity that we all know, right? From small scale systems like calculator to really large scale to supply a small city. These have been installed around the world. Clean energy, very good. However, actually, I would like to find out if anyone, perhaps a student who will venture a guess as to what fraction of electricity used, maybe in the UK or in the world or anywhere, that comes from solar energy. Anyone care to guess? 2, 7, any?
Less than 1.
Okay, less than 1. All right, so indeed, worldwide is 1 or less. I don't know about the UK. In the US, is barely 1, so roughly 1 or less. So very poor. Even though we know this is pollution-free, very clean, but they are not used. I don't have to ask you why they are not used, right? It's the cost. Because they have been too expensive compared to fossil fuels, right? From oil or gas or coal. Okay, so what is motivating work in the area of organic photovoltaics is to explore new approaches, new materials, new ways of fabricating photovoltaic devices and systems in a way that can potentially, substantially, perhaps by orders of magnitude, reduce the cost. For example, perhaps by using technology quite familiar with plastics and newspaper, like roto printing and such techniques. All right, so this is a very old, busy slide that collects all the efficiencies of, at research level, laboratory efficiencies of solar cells of different classes of materials. In fact, right now, it's above 40% for the more exotic inorganic semiconductor materials. And even at this level, if you look at this, what you will see is that there are many, many materials that have very high efficiencies in these devices. Organic photovoltaics, down here, relatively low. And obviously, one reason is that it's relatively new technology, but there is more to it than that. Okay, so the reason why organic solar cells are relatively low is that, in fact, the physics is quite different compared to the physics of inorganic semiconductor-based solar cells. And in fact, when you shine light on organic semiconductor, whether in the device or in a film, what you create with the light, with the photons absorbed, excitons, electron-hole pair that are bound together very strongly with binding energies that are quite large, which you have to find a way within the lifetime of the excitons to break up and collect the charges as current. Another very important characteristic of excitons in organic semiconductors is that they don't move very far. The typical diffusion length is in the range of 10 to 20 nanometers. Okay, so they don't move very far, which means that within the few nanoseconds or so that they are created, you have to find a way to break them up. The scheme that has been found to work the most efficiently is to bring together two different organic semiconductors, one called a donor and the other called a acceptor, that have energy levels as indicated, highest occupied molecular orbital, or HOMO, and then the corresponding LUMO here, staggered in this way. And then upon shining light on it, you will be able to get photo-induced electron transfer to take place. So that means that at this interface, you have to generate excitons that are within this exciton diffusion length. So this length basically provides a scaling for the systems, meaning that they are necessarily nanostructure systems if they're going to be efficient. And this is one of the big challenges in the field, to make efficient organic photovoltaic devices, as we shall see. So typically, this is a typical solar cell. So you have two electrodes, the active layer, and over time there has been evolution of what that active layer should be, the organic semiconductor active layer. What has been found in order to indeed create these interfaces between two materials, the donor and the acceptor, is to have a blend, otherwise known as a bulk heterojunction, so that if done properly, then you have sufficient interfaces to have efficient devices. All right. The typical measurement that we do from a solar cell like this is the current voltage characteristics, from which we are very interested in, for example, the open circuit voltage and the short circuit current, from which we can figure out the power conversion efficiency, or PCE. You will be seeing these metrics as we go along, and some of the big challenges in the field, in fact, is really trying to understand and control these polymer blend systems, or bulk heterojunction film of these materials. All right. So you have the polymer and the Fullerene blend in solution, and you want to make a film to create the bulk heterojunction so that you have the interface between the donor and the acceptor material. What has been studied the most initially were these polymers in combination with the Fullerene derivative shown here, PCBM. One of the key challenges is how do you control the phase-separated morphology of this blend thin film. Okay. One is, can you really control the domain sizes so that you are within the exciton diffusion length? Can you really get charges to find their continuous path from one side to the electrode, the respective electrode? And even if you have a very nice nanophase separated structure initially, what happens over time? Will you have domain coarsening? And indeed, that can happen, as demonstrated here, that the original morphology shown here becomes these over time, which is not good, right? Especially for devices that you hope that one day you'll be able to put on a roof for many years. All right, so at the heart, one of the big challenges in the field is really how to control the morphology of the bulk heterojunction active layer in these devices. So there are a number of approaches that have been taken. I have just two examples here. So one is, excuse me, one is to use different conditions to control the phase decomposition process, the drying of the solvent away from the film. And these, to varying degrees, can have some control, but what is shown here for this particular polymer in using the PCBM that you have seen earlier, that if you simply spin coat a film and you leave it to dry at room temperature, this is the kind of structure that you have, very large domain sizes leading to very poor efficiency. On the other hand, by adding some additive to the process, and then, here, just taking the same film and drying it very fast in vacuum, you can improve the efficiency. On the other hand, if you add additive and you age by drying slowly at room temperature, you dry in vacuum very fast, as you can see, you structure it more so that the domain sizes are more in the nanoscale, and that improves efficiency of devices. Another approach that we have explored in our lab is trying to use a molecular self-assembly process by pre-organizing or pre-assembling the polymers in solution and then mixing the Fullerene. The idea being that the self-assembly wire, you've already limited the size, and it has worked to some extent. So, for example, such nanowires for this particular polytauphene are shown here. The wires are on the order of 10 to 15 nanometers, so ideal within the exciton diffusion length scale. quite crystalline, so presumably it should be able to transport charge very efficiently. All right, so here, by mixing then the fullerenes with the polymer nanowires, we demonstrated that we can make devices that were a lot more efficient compared to devices where you simply spin coat the film and let the phase decomposition be uncontrolled. All right. We have used this approach a lot to try and do fundamental studies, particularly in collaboration with my colleague David Ginger in chemistry at University of Washington, where we were able to combine bulk characterization techniques with nanoscale characterization techniques such as photoconductive AFM or conductive AFM to really look at the nanoscale when you shine the light on the active layer and you are generating electrons and holes, watch where the holes are going, where the electrons are going. And we have extensively used this way of controlling the morphology to try and get a handle on some of the fundamental aspects of these devices. All right, so in terms of really trying to address how can we make more efficient devices by designing better materials. One of the approaches has been to obviously fix the fullerene PCBM while finding ways to vary the electronic structure of the donor polymer. And in doing so, one of the this was a quasi theoretical calculation in trying to help in the design of or answer the question, for example, what band gap or what absorption characteristic in a donor polymer will lead to what efficiency of a polymer solar cell. And what is interesting is it was determined that if you use PCBM as the acceptor material, that the donor that has a band gap on the order of 1.7 electron volt or so, with a corresponding LUMO in this range, will probably be a good target to be able to reach 10% power conversion efficiency. And so many people have subsequently tried to follow this approach in trying to design material. The approach doesn't work very well, but it has provided some guide, and we and others have used it to try to design polymers that can at least shed light on how we can improve device efficiencies. All right, so what I show here, we're not going into the details of the chemistry of making these polymers, but the basic structure is shown here. What we were particularly interested in was to tune energy levels and therefore the band gap and therefore the absorption characteristics. And what you can see is that we have the LUMO relatively fixed while varying the HOMO over quite some range. And what we hope to be able to do with this, and what we have done, is to, from this library of materials that we have generated, select groups of these materials to try and extract structure property relationships from such a cluster of materials. And in this way, we discover one polymer and relatives in particular. The structure is shown here. This is the backbone of the polymer, and we have different side chains attached to it. And this is what it looks like, a very wrinkled freestanding film. And of course, we can deposit more uniform film by spin coating. This was just cast to look at the characteristic of the material. So what we find in this particular grouping of three related polymers is that the polymer with branched side chain has very close absorption. As far as absorption, all three are about the same. However, it has some very, very interesting characteristics that are quite different. The way it packs in a solid state. So from X-ray diffraction shown here, very, very simple X-ray diffraction, we can see that of the three, this particular one, PSCHTT, it tends to pack in such a way as to have efficient pi stacking in a particular direction, which is quite different from the other two. And in fact, I show it here better, that in the case of PSCHTT, it tends to pack such that the molecule lies on the substrate and pi stacks like that, so that the pi stacking is is perpendicular to the substrate, as opposed to the other two polymers with more linear side chains, where they pack edge-on, so that the pi stacking direction is parallel to the substrate. This is actually very important for solar cell applications, because in fact, this is what we would prefer if we were to know how to do it. We don't really know how to design a polymer that will preferentially pi stack that way. This we discover by having a large library, and by experimentation, we found that this polymer packs that way, but clearly suggesting that perhaps by doing side chain engineering, by keeping the backbone, and you do side chain engineering, that could be one way of searching for polymers that are going to be able to pack in this way, because we do know that that kind of packing leads to better photovoltaic efficiency and better performance, as indicated here in a combination of charge photogeneration studies done in collaboration with the Durant group here at Imperial, and devices that show that indeed PSCHTT among the three has better photovoltaic properties that can be clearly connected to this ability to pi stack in the face-on motif. All right, so let me skip this and quickly tell you about a couple of other areas and recent results from my group. So for a very long time, I would say the last 25 years or so, progress in the field of polymer-based solar cells are different on fullerenes. The polymer had changed, so there's evolution of the donor polymer material, but we have always relied on fullerenes as acceptors. And in trying to understand and study why fullerenes have been so good as electron acceptors, a number of theories have been established. But I'm going to skip this and basically point out that we have known for a very long time that fullerenes are not ideal for a variety of reasons, and here are some of the reasons. I'm not going to go into all of this. Poor photochemical stability, which has implication for stability of the devices a long time. They're also very expensive, very expensive. Actually, 1 gram of fullerene more expensive than gold, right? And the goal is to make these devices very cheap. So, all right. So we have every reason why we would like to or should explore alternatives to fullerene. So, in my lab, we have done a lot in this area, exploring both small molecules and polymers in hope of finding alternatives to fullerenes. One particular class are the early dimers, DBFIs, made by a very talented postdoc, Haiyan Lee, shown here, in which we have shown that each of these molecules, in terms of the area or the phase that it presents to a donor polymer, is comparable to 9, the equivalent of 9 fullerene molecules. And we've also, from DFT type calculations, found that these dimers have more electron accepting states compared to fullerenes. And in fact, in devices for the first time, we discovered that they can be more efficient than fullerenes in head-to-head comparison, of which such comparison is shown here with this tauophin-linked dimer, with this polymer PSDHT that you've seen before. And clearly, this polymer with DBFIT shows is more efficient compared to this polymer with the fullerene PCBM. And in independent studies with materials, actually blind studies at Osaka University, they currently could predict the order of efficiency that we actually observe in Seattle by doing time resolve microwave conductivity type measurements. All right, so then we decided to try and tune the three-dimensional structure and see how that impacts the electron accepting properties and the performance of these devices. And okay, sorry for this is very busy, but what we basically found is that by using different liquors, while everything else is fixed, the electronic structure very similar, and the absorption characteristics very similar. However, keep in mind there's the geometry or the twisting of the two building blocks within the dimer is varying a lot. So, which has implication for how in combination with a donor polymer, it might behave in actual devices. Let me skip this and go directly to the results. So what we find is that indeed in devices, these dimers lead to very high efficiencies compared to where the fullerene is now shown here. But we are using this dimer with E-dot Leica, pairing it with these two different polymers, and to basically show that we can use these non-fullerene electron receptors similar to fullerenes with different donor polymers and get very high efficiencies, and in particular the photovoltages are quite high compared to what we normally can get with fullerenes. All right, so with a little bit of optimization, we can get these devices to now about 9% or so, which are better using the same donor polymers with fullerenes, but certainly comparable to where fullerene-based organic photovoltaics currently are. And so we're very excited about the new pathway opening up here to critically look at non-fullerene systems where this could take us in the field of organic photovoltaics in the future. So if we plot the efficiency, PCE as a function of the twist angle, this is purely empirical. We don't have any theoretical basis, but it appears to be linear. And the obvious implication that one can see here is that perhaps if we go to 90 degrees angle, are we going to get to the close to 11% or so predicted from here? We are currently at work in trying to test this idea. Okay, and this is the work of a very talented graduate student, Yejin Huan, who graduated last year, now a postdoc at MIT. All right, so it looks like we are going to be running out of time. So I don't know, another 5 minutes to wrap up. All right, so the last example that I wanted to share with you is actually right at the beginning, the idea of using fullerenes in polymer photovoltaic devices was published in the same year as the Cambridge group that had the idea, well, what about using a purely all-polymer system where the acceptor will be a polymer, the donor will be a polymer, as indicated here. However, the field of polymer fullerene systems and devices has dramatically advanced over the years than the all-polymer devices for a variety of reasons. The main one being that it's very difficult to find N-type polymers, acceptor polymers that can function as good acceptor materials. Another problem is one illustrated here, which is we develop this naphthalene-diamine-based polymer shown here, PNDIS-HD, which is fairly crystalline, and it has relatively high electron transport characteristics. When combined with the polymer here, the donor polymer here, which is known to be a high-performance photovoltaic polymer in the realm of Fullerene devices. However, what we found is really bad, with efficiency of only about 1% or so. So in looking at the details, so even though the energy levels are such that one would have thought that this is perfect, and the absorption characteristics are also very good. However, the results shows that this is a bad combination. In other words, this is not a compatible polymer blend system. So we looked at the morphology and discovered that in this blend system, it tends to phase separate on relatively large scale. No matter how we try to control that, we never could really get them down to domain sizes in a nanoscale range. And we thought that the reason for this is likely due to the fact that the two components, the acceptor and the donor polymer, they both are highly crystalline material. So we decided to, all right, let's try and change the crystallinity of the acceptor material by making random copolymers, such as this shown here. And indeed, by doing that, we can progressively change both the degree of crystallinity and the crystallite sizes, or the coherence length of crystals. And in the process of doing that, by incorporating paralleling-diamine or PDIs with naphthalene-diamine in the structure shown here, we also see that the pi stacking distance is significantly changed. However, the electronic structure is not changed a whole lot, and there's slight changes in the absorption characteristics. However, this leads to a huge change in the morphology of the blends, as we can see here. So going from the original, where we have the large nanoscale separated structure, as we incorporate more and more of the paralleling-diamine, so you see that the domain sizes go down. And in the case of the 50%, they become very, very small. However, in device performance, it turns out that the 30% PDI in combination with the same polymer in all of these gave the best result, as shown here. In fact, more than a factor of 5 enhancement in the efficiency by finding a way, in this case, through random copolymerization or making random copolymers, where we are able to regulate the crystallinity, we are able to achieve more compatible polymer blends in making all polymer solar cells. All right, so let me close by pointing out clearly the future of carbon-based electronics is quite bright, with the appearance of graphene nanoribbons, which are semiconductors, but orders of magnitude higher than crystalline silicon. If we can develop methods to make such graphene nanoribbons, that in my view they are simply 2D conjugated polymers. So they are targets, and in fact we have a project in our lab exploring this. So finally, I tried to show some examples, results in our lab where we have used molecular design and synthesis in combination with trying to control nanostructure and engineer devices, OLEDs, and photovoltaic devices, and in the process try to understand the structure, property, device performance relationships. All right, so many current and former students have contributed to some of the results that I showed. Many agencies have supported my work in this area. So let me stop here. So hopefully there will be time for some questions. So thank you very much.
I think we have time for some questions.
One of the self-inflicted problems of sitting at the back is that I couldn't see what typical absorption lengths were for these materials.
Well, yes. So the thicknesses of the films were typically 100 to 120 nanometers, and the absorption coefficients typically at the peaks typically 10 to the 5 per centimeters. So from that you can get the information you want.
Could you say something about expectations for lifetimes? Because thinking about energetic holes plus hydrocarbons, I would have thought that's a recipe for problems.
So let me get this straight. So lifetime of all right. So the question is, what about the lifetime of these devices? That the expectation would be that the fact that we are using carbon means that there will be a problem. Okay, so as an example, I think exactly the same issue was raised with OLEDs, or organic LEDs, where with proper packaging of the devices, lifetimes exceeding 100,000 to 150,000 hours have been demonstrated. So I certainly expect, although there are different processes in the case of photovoltaic, I expect that should be quite possible with organic photovoltaic devices.
So, Sam,
yes.
Thank you very much for a very interesting talk. I was wondering, looking at the evolution of the polymers that you had worked on, if you could comment on the scope for in silico design of the materials versus just making them and testing them. It seemed to me that some of those were quite complex structures. I guess that it might be quicker to actually make them and test them than to try and calculate how they would work. But maybe you could comment on whether you think there's any role for molecular design of materials in
Yes.
silico.
Yes, I quite believe that the field definitely needs that kind of effort, and there is very little of that at this point, where the design amounts to using a combination of intuition from chemistry and experience of similar compounds that people have made, as well as perhaps a very simplistic DFT type calculation in terms of energy levels, absorption characteristics. But what I think will be very helpful is really being able to predict more than just energy levels, being able to predict are these materials going to be crystalline, how are they going to pack. So the example of the PSCHDT that packs face on that I mentioned, or pack edge on, which can be useful for other purposes like transistors. But for photovoltaic, this is the preferred packet characteristic that one would like. Yes, I think there is a role there that has not been taken up, perhaps because it's very challenging to do. We don't do a whole lot of simulation in our group beyond using commercial package DFT to look at energy levels and so on. So it's a very important area that I think we're going to need if we really are going to take these systems to the next level, that they will be able to be produced more efficiently on a large scale.
I think one more question. Your last one.
All right, it will be a layman's question. It will be a layman's question, so thank you for allowing me. But photovoltaics hold a great hope for humanity, particularly for the underdeveloped world. And I would like your impression. Are we doing enough research on these issues? Thank you.
Okay. I think from my perspective, it's very easy to say, no, we're not doing enough. I mean, particularly, certainly in America, in the US, that politicians are not very fond of long-term commitment, particularly when there are fossil fuel constituents, coal. There are some regions of the world where coal, oil, and gas are very important, and they would like that to be around as long as possible. So, no, the work, there's not enough work being done in this area. Having said that, some countries are doing more than others. So, for example, China, they have a lot more activity in this area, even more than the U.S. For example. So ultimately, this is the most abundant source of clean energy with low-level risk compared to nuclear for energy, for example. So sooner or later, I believe that we will have no choice but to invest in really exploring to the fullest possible that we can.
And with this last question, I'd like all of us to thank Professor Jenekhe for a wonderful lecture. Thank you. Thank you. We have a very small gift for you. something to remember Imperial by. Thank you again.
Thank you.